Hi, this is Brandon Baines in the Math Department at Lipscomb University, here to talk with you today about applications of systems of linear equations. In this presentation, you'll learn how to solve systems of equations in applied settings. Here's an example. A bicycle shop has 36 bicycles and tricycles combined. When the wheels are counted, there are 80 wheels in all. How many bicycles and how many tricycles are there? This is a classic problem I give in a problem-solving context because there are lots of ways we can approach this problem. Some students may begin by guessing the number of bicycles and tricycles and seeing how many wheels they have. For example, I could try 18 bicycles and 18 tricycles because that would give me 36 in all. And then I can count the number of wheels. I would see that that's not the solution because I don't have 80 wheels, and I could adjust from there. The nice thing about algebra is it allows us a way of considering all of those combinations of bicycles and tricycles all at once with our equations. And so we'll choose to write some equations, and we'll talk about what we can do with those equations to solve this problem. Since we know that there are 36 bicycles and tricycles combined, if we let x equal the number of bicycles and y equal the number of tricycles, then we have the equation x plus y equals 36. The second requirement is that there are 80 wheels in total. And so each bicycle would have 2 wheels. Each tricycle would have 3 wheels. So we have the equation 2x plus 3y equals 80. This forms a system of equations because both of these equations must be satisfied. One of our methods of solving systems of equations is to graph and identify the ordered pair where the graphs intersect. And so you see the graph below, and we can see that those two lines do intersect. This is the graph of both of those equations. We looked at a zoomed in picture, we might be able to identify the ordered pair better. I see that on the x-axis, this is the x value 28. And on the y-axis, this is the y value 8. So there must be 28 bicycles, since x was representing the number of bicycles, and 8 tricycles. Sorry, didn't want to move on just yet. Keep in mind that we could have also solved this system of equations using substitution. We could have also identified the ordered pair 28, 8 on their xy tables of both of those equations. There are lots of ways we could have arrived at 28 bicycles and 8 tricycles. Here's another example. A young child is currently on a diet of milk and cereal. The milk has 8 grams of protein per serving and 150 calories per serving. The cereal has 5 grams of protein per serving and 120 calories per serving. The young child's diet requires that she consumes 58 grams of protein per day and 1,140 calories per day. How many servings of milk and how many servings of cereal should she eat? Keep in mind here, there are lots of ways we could attempt to solve this problem. One of those is to begin guessing and checking with servings of milk and cereal and seeing if the needed requirements are met. It's actually a really helpful thing to do because it will focus our attention on the things that this problem is considering. And in this case, that is milk and cereal. That's what we're working with combinations of. But we're wanting to satisfy the number of the number of grams of protein and the number of calories. And so that actually can be very helpful when we go to write equations, if we choose to write equations to solve this problem. If we've done a little groundwork of playing with the numbers first. We will write some equations for this scenario. So consider that the young child needs 58 grams of protein per day and the sources of protein come from milk and cereal. So we can write the equation 8 times x plus 5 times y equals 58. In this case, I'm letting x equal the number of servings of milk, and y is the number of servings of cereal, and 8x because 8 grams of protein per serving of milk, and 5y because 5 grams of protein per serving of cereal. Second, the young child needs 1,140 calories per day. And so we have 150x plus 120y equals 1,140. And again, the choice for a 150x is because each serving of milk has 150 calories. And the choice for 120y is because each serving of cereal has 120 calories. From here, we could graph these on the xy plane and identify the ordered pair where they intersect. That would be a fine way to solve this system of equations that has been formed in this scenario. We can identify that we're solving a system of equations because we have two equations that we need to satisfy. That is, we need 58 grams of protein, and we have an equation for that. We have a calorie equation. We have to make sure that that's met. We'll do substitution to solve this problem. And so we'll follow the steps outlined in the previous presentation. Step 1, we'll choose 8x plus 5y equals 58, and we will solve for y. That results in negative 8/5 x plus 58/5. Remember, with substitution, we now have an equivalent way of saying y. We have negative 8/5 x plus 58/5. So our step 2, we will substitute that value of y into the other equation. So that was our calorie equation, 150x plus 120y. But again, this is the same as y. And that should equal 1,140. Step 3, we'll clean up and solve for x. So we're going to first distribute the 120. That results in 150x minus 192x plus 1,392. That's equal to 1,140. We'll combine like terms, and we have negative 42x. That's a result of subtracting 192x plus 1,392 equals 1,140. To solve this equation, we'll subtract 1,392 on both sides, as well as divide by negative 42 on both sides. And that results in x equals 6. The interpretation on that would be 6 servings of milk, since x was representing the servings of milk. Step 4, we'll substitute this value of x into any of the equations. I'll choose the equation that we formed in step 1. When we do that, when we let x equal 6, we find that y is equal to 2. And so the young child needs 6 servings of milk and 2 servings of cereal per day in order to meet the requirements for protein and calories.